So I'm Ken Raffenetti. I'm a software developer at Argonne National Laboratory in the Programming Models and Runtime Systems group. I'm here to talk to you about interconnects. By interconnects, I mean kind of off-node communication. So we've kind of seen, throughout the day so far, kind of on-node architectures. So now I'm going to talk a little bit about off-node and the network adapters and network technologies that supercomputers use to achieve communication between nodes. I'm an MPI person by day. I work on the MPI-CH MPI library. So this isn't going to be an MPI talk. I know Scott mentioned I might be talking about MPI, but I think that's coming later in the week. This is going to be more kind of a step below MPI, so kind of what's going on in the machine itself that kind of MPI is able to take advantage of and you're able to use through the MPI interfaces themselves. So just to start, this is a slide, a slightly modified slide from a DOE exascale report about kind of trends in system architecture. And so this is kind of, it's got machines from the 2010 era versus, these were predictions about 2018 at the time. Now these have kind of come to be realized in machines today, and they're reasonably accurate if you think about, the Summit machine that has, 40 teraflop node performance and has, on the order of thousands of nodes. That kind of matches up with the predictions here. The left side of the split in the 2018 section is kind of what a lighter weight node looks like today. I think something like, if you think of theta, that kind of looks closer to that, though we don't have quite so many nodes of theta at Argonne today, but maybe a machine like the Taihu Light machine in China might look pretty close to that as well. And then out in the exascale time frame, so 2021, which is when we're expecting to see exascale machines start to get deployed in the U.S. We can kind of project out and think about where things are going and how that's going to affect specifically in this talk, how that affects kind of the interconnect technology. So the takeaways here that we have are that the number of nodes is increasing, but kind of not that fast, at a moderate pace. But the number of elements, the number of cores, threads on a node are increasing rapidly. We're definitely seeing that. We have 60, some odd cores on a node, plus whatever accelerator cores and things like that. So there's lots and lots of concurrency on the node. Those cores aren't necessarily increasing in speed. The clock frequency is staying more or less stagnant, or in some cases we're seeing slower cores, which kind of follows into the next bullet here, where the chip logic complexity in some cases is actually decreasing. We're seeing more specialization in the chips as opposed to these fully generalized power-hungry cores, and so that does have some effect on the interactions with the network as well. So what does this mean actually for networks? Well, we're going to have to be driving the network with more cores. That kind of goes without saying. That means more sharing of that network infrastructure. If you saw the architecture diagrams, now we've got tens and some 60 some odd cores on the node, all kind of funneling down to one or two network adapter links. The aggregate communication, I mean, this is kind of a prediction, but the aggregate communication of a node, that's going to increase somewhat now that we have, there's more data, there's more computation happening on the node. But what's actually going out is going to be only moderately bigger, we expect, but we do expect maybe smaller messages. So we're seeing more communication, but kind of finer grained. If you think maybe in a strong scaling scenario, something like that, where there's more smaller messages, being pushed onto the network. And something that's true today and is definitely going to be true in the future is that a single core is no longer able to saturate a network link by itself, that you're going to have to take advantage of parallelism on the node in order to drive the network drive the network fully. So again, before I dive into kind of the agenda of this talk, we're gonna, the talk is kind of laid out in such that, the way node architecture has changed up until this point, and then kind of ways we see it changing in the future, and how that relates to network performance. So this is a simplified diagram of what a machine might have looked like 20 years ago or so, where you kind of, you've got your CPUs, you got your memory, you got some I/O bus that's connected, your network adapter is connected to, and then that goes out, onto the greater network as a whole. And all of these kind of, all of these points kind of introduce potential bottlenecks into the system. And so, you have bottlenecks at the cores, at the memory, at the I/O bus link. The network adapter, the switch might have, certain communication bottlenecks. So it really took a good balanced approach, in the old days to realize, decent network performance, at least perceived network performance, because there were all these kind of potential pain points in the system. And so I'll kind of go through each of these as the talk goes on, that shows, where things are today, and where the bottlenecks kind of remain. So, like I said, I'll go through a quick agenda here. First thing I'll focus on is what network adapters are kind of, how they're integrated into the system today, what they're capable of. I'll spend a little time going over network topologies, specifically ones that you'll see in HPC systems, and then a little bit about the interactions between network adapters and their interactions with processor and memory on the system. So the first bottleneck we'll look at is the network, the network link bottleneck, the network link performance in a system. So this is really old, early days stuff. So if we think about some of the first commercially available network technologies, you look at Ethernet, which was made available in the late 70s, and it ran at 10 megabits per second and did so for over a decade, and no one seemed to have too many issues. And then I think, so sometime in the 90s, probably, around the time the internet started to become more popular, that there started to be a little more acceleration in the development of improved network link speeds. So if you think about fast Ethernet, gigabit Ethernet, those kind of came one after the other in the mid-90s. And other network technologies, more specialized network technologies like ATM networks, MirrorNet, Fiber Channel, also came about around that time. So there was a lot of advancement kind of in that time frame. Fast forward to today, there's been a lot more advancement in the meantime. Today's network interface speeds are maxing out at about 100 gigabits per second. So if you think about the Summit machine, it has 2 InfiniBand EDR links per node for aggregate bandwidth of 200 gigabits per second. We don't see this slowing down at the moment. In fact, there's pretty conservative projections is that we'll see 200, 400, up to terabit signaling on a single network link sometime in the next few years. So that's something that we'll probably see in that exascale time frame, maybe going beyond 100 gigabit per second. As I mentioned, multiple network links are becoming commonplace on HPC systems. Summit and Sierra both have kind of dual rail InfiniBand. The Japanese post T2K machine also multiple network links. Also Taurus style networks, things like that already have kind of built-in multiple links. So that's something that is definitely more commonplace these days. The next bullet, when we say end host peak network bandwidth is mostly no longer considered a limitation. Is that again, I don't have the diagrams like in the Summit talk, but for the most part, pushing being able to fully saturate, pushing enough data onto the network is kind of not an issue anymore. That the network is able to handle whatever the nodes, whatever the applications are throwing at it. So, and if it needs more bandwidth, more aggregate off-node bandwidth, we can just kind of add more links. It does incur some cost, but if that's what works best for applications, that's mostly possible. Latency is where things are a little bit more difficult. So network latency is harder to solve just by throwing money at the problem, by adding more links or more network adapters. With latency, you're kind of more limited by physics. What the speed of light is, how fast you can actually send signals from one place to another. So today, there's a little bit of room to improve in network stacks. We can kind of write leaner software, cut out more specialization, cut out more some of the general purpose things that right now are kind of adding to latency. Something else you can do is kind of make systems denser. So there's actually physically shorter distances for signals to travel before, so that hopefully the latency can be lessened a little bit. And on top of that, so these things kind of lead into important metrics to think about when considering your network interface speeds is how many messages, what's the actual message rate capability of a card? Not just the bandwidth, but how many messages could it send out over a given amount of time? And how does it deal with congestion? How does it handle when lots of other machines around it are communicating at the same time? So again, we go back to our kind of simple diagram where everything's decoupled, and then what's happened this is not a recent advancement, but what has happened over the years is that we've seen the memory controllers integrated onto the chip. This is the NUMA architecture that you'll see on almost any machine today. And so the primary purpose of this integration was to help with memory bandwidth limitations. But it does also help with network communication. So data transfer to and from the network requires some coordination with the caches themselves. So having this kind of more tight integration allows the network to kind of work better with the memory, as opposed to having to having to coordinate kind of separately with everything else. But we still have this I/O bus here. So there's still this kind of disconnect from the network adapter, or from the CPU to the network adapter, and there's obviously a number of technologies that are able to connect network adapters with the CPUs today. PCI Express probably the most common, the one that you'll see with most adapters in systems today. And for now, I think these I/O technologies are kind of, they're doing okay when it comes to providing higher bandwidth than what the network underneath is able to provide. So for now, the I/O technology is good enough that we don't have to worry about not being able to fully saturate the network underneath. But what about the future? What else are we? Not just integrated memory controllers, but what else do we need to be thinking about? So we say current/future in this slide because some of this is actually possible today. So a lot of vendors are looking at integrating the network adapter right onto the CPU as well, kind of eliminating that I/O link from the previous diagram. And I think today you can actually buy a K&L, a Xeon Phi with the fabric actually integrated onto the chip itself. I think there is still kind of a PCI Express connection, pseudo connection there on the chip itself, but it is at least physically closer, and maybe that boundary will kind of go away in the future. really know, but I'm kind of hoping so. But this type of integration of network interface onto the chip, again, should, in theory, improve the network latency, you know, with everything kind of closer together, more tightly coupled. And what we hope in the future is that we'll actually improve the network functionality itself. Whereas before, and you know, in the previous diagram, you would think of network communication as kind of a second-class citizen. It's sitting there across the I/O bus, and you kind of, you know, send data and commands to it, and it kind of handles things on its own. Now here, there can be a little bit more coordination. Specifically, one example we can give is that, you know, there's atomic operations that are supported by the network hardware. There's atomic operations supported by the CPU hardware. But these atomic operations are not atomic with respect to each other. So if you know, a CPU atomic happens at some point in memory, and then you want the network to operate on the same same location in memory, then you can't predict what's happening. You could, you know, it's not, they aren't atomic with respect to each other. But you could think that if these network interfaces, if these network chips get further integrated onto the package, then we could potentially see that capability where they are atomic with respect to each other, and that could be pretty exciting from a distributed memory programming point of view. So that kind of takes us through network adapters and where we kind of see things going. Now, in terms of software, what we call processing bottlenecks. So back in our old diagram here, what's, you know, essentially what are the bottlenecks that the CPU runs into when in the course of network communication? So example here are network protocols like TCP and UDP, essentially software protocols. The design of these old style network communication protocols kind of assumed that the networks themselves were dumb. All they could do was kind of push packets in and out of the network card, but all the kind of protocol information was encoded in software. In this case, you know, the CPU is kind of in charge of handling most of the aspects of communication. It's doing the data buffering, it's checking for data integrity with checksums, it's encoding the routing information and so forth. And then internally, inside the software, you know, inside between the OS and the application layer, there's lots of signaling going on about, you know, packets coming in, you know, packets going out, data being ready, data being retransmitted, things like that. So, you know, if you think about old machines where network protocols were mostly handled in software, this could quickly become a problem where instead of your CPU working on the actual, you know, number crunching that your application is being designed to do, it's spending all this time kind of handling network communication, which is less than ideal. So when we think about HPC systems of today, we think a little bit about how we're now able to offload some of this traditionally host-centric protocol, network protocols work to the network hardware itself. And so today, modern networks are spending more and more of their, you know, kind of their chip real estate offloading these various communication features. So things like reliability, packetization, those things kind of happen in hardware as opposed to on the CPU, or on the network hardware as opposed to the CPU. And then I say a little bit here about OS. I have some slides later on about what I mean by OS-based memory registration and user-level data transmission. So this is kind of important also to the overall performance picture of today's networks, is that particularly the user-level data transmission is something that is able to some performance gains over the previous generation of network protocols. So here's just kind of a comparison of an old, kind of a traditional network protocol stack. If you think of something, again, probably a traditional Ethernet with TCP, TCP/IP on top, you've kind of got your various layers in the architecture diagram. From the application perspective, applications would operate over a sockets interface, something like that's available in most operating systems, where you kind of read and write data into a pipe, and then it would get kind of pushed onto the network and communicated to the remote endpoint. In a more specialized environment, like HPC environment, we have a lot of the same layers, but some of them serve some different purposes here. So you can see that there's some management tools actually incorporated into the link layer of an HPC network. The network layer is mainly just in charge of routing. This would be kind of switches and so forth. At the transport layer, we have both reliable and unreliable protocols, similar to TCP and UDP, but they're more specialized. Because again, when we think about HPC systems and their interconnects, we're not thinking about, again, a fully generalized protocol that works, that works on internet scale. So, internet scale protocols have a lot of generality, a lot of kind of redundancy and reliability built in, whereas, in HPC, we're talking about maybe 10,000 nodes, tens of thousands, maybe up to 100,000 nodes in exascale systems. We really don't need all of that, all those bells and whistles and safeguards from those general purpose protocols. So specialization is one thing I think you'll hear throughout all these architecture talks, is that in HPC, there's a lot of specialization, and that's particularly true at the network layer, that when we're building these interconnects, this is really kind of a specialized thing that works just inside a kind of a small cluster of machines. And so as opposed to a sockets interface, we have some lower level interface, and I have a slide later on talking about what those interfaces kind of look like today, what the kind of major players in that space are. Then on top of that, at your application layer, you're using things like MPI or PGAS in order to actually interface with the network itself. So as opposed to on the left side, where you've got more webby technologies like HTTP, HTTP and so forth. And so, yeah, when we're talking about offload, here almost everything is being handled by software, whereas everything up until this point in an HPC system we're starting to see offloaded into the hardware itself. So yeah, I touched on this in terms of network APIs. So again, we've kind of, in HPC, we move beyond sockets, and we're working with kind of lower level interfaces these days. Things that you may have heard of, there's lots of vendor specific or non-vendor specific APIs out there today that handle network communication. The popular ones being InfiniBand verbs, Intel's PSM2 library, which works on their OmniPath hardware, IBM PAMI for Blue Gene machines, and Cray has their own network APIs as well. There are ongoing efforts to standardize these low-level communication APIs to make things easier as kind of new networks are kind of being released, and they're making it kind of less effort to port all the MPI and PGAS code to new machines by kind of standardizing on interfaces that, in this case, kind of just define abstract network functionality. And therefore, those get integrated into MPI libraries and PGAS libraries, and they kind of handle the hardware details for new technologies inside these abstract library. So the one I have at the top here, Open Fabrics Interface, or OFI, also referred to as libfabric, if you've seen that around. This is an effort out of Intel and Cisco and some others, really the Open Fabrics Alliance. And this is their effort to kind of provide a unified interface for low-level communication that exposes the features that a network provides. So with OFI, if you were going to write OFI code, you would kind of query at initialization time, what is my network hardware underneath? What it is able to provide? First, what all network technology is available to me? Then what do they provide? And I can kind of pick and choose from there how I want to run my application, which features are important for my code to run efficiently, or what do I need to run at all. A parallel effort to OFI is this thing called UCX, Unified Communication X. This is from a different group of vendors, though I think there are some overlap in some cases. But Mellanox, IBM, Oak Ridge, and others, it's a similar idea. We have low-level communication layer that's built again to kind of support these MPI or PGAS APIs on top. The difference in UCX is that if a feature can't be provided in hardware, there is always software emulation, so that the full UCX API the full UCX API is always available regardless of the hardware that's underneath it. Whereas in OFI, that's more of we just expose what the hardware is capable of doing, but we don't emulate in software. We leave that kind of up to the middleware, up to the application to do. And then the third one here, which is a little bit different than the previous two, this is Portals 4. This is a project from Sandia National Laboratory. This is really more of a hardware specification than it is it is a network API, but it's more of a hardware specification. So Portals 4 describes essentially the features that an HPC network should provide in order to support all the applications that are going to run on it. So it describes two-sided messaging semantics with tag matching, specifically for MPI, but it also does one-sided operations like put-get to support both PGAS and MPI one-sided APIs. And so, as I mentioned before, as we showed in the diagram, how everything but kind of the user level portions of the network stack are offloaded in hardware. So what's left? What's the user level responsibilities in order to perform communication on these interconnects? So this is a diagram of what happens when we perform what we call memory registration. So memory registration is important for RDMA networks specifically, remote direct memory access networks specifically, because it ensures that the memory addresses that you're communicating in and out of are going to be kind of pinned in the memory, in the physical memory, so that when the network adapter goes to communicate in and out of them, it can be confident that that's the correct data is there, that the OS is not swapping pages in and out of the physical